All right, here in this video for fluids, what we're going to talk about is shear stress and viscosity. So stresses are caused by forces in fluids. We have kind of a somewhat confusing notation for how we can handle, say, some arbitrary force like this acting on a fluid. That's going to cause stresses in all of these multiple directions. Some of them will be normal stresses, like these guys here, and some will be in the plane of that surface as a shear stress, right? Normal to the plane or in the plane as a shear stress. And again, we identify the plane that they're acting in, and then the second dimension is the direction that they're acting. So if we put all of this together, we can talk about what's called a stress or the stress tensor for a fluid. And what this is just a kind of complete picture of how fluids respond to stresses. So we have right here the I direction, the J direction, and the K direction. And here this would be the YZ plane. This would be the XZ plane, or again, Y is the outward normal. And the last one, Z is the outward normal, so it'd be the plane in the XY dimension. We're not going to talk too much in detail about the stress tensor, but it is, in general, if you have a general force acting on a fluid, we get all of these different stresses inside. So this is going to be important for understanding how fluids move, right? How they respond to forces. So we're going to go back just a little bit in time to our good friend Newton. So what Newton observed, is that most fluids under normal conditions behave in kind of a similar way. So if you look at a system like this, where we have a force applied and there's a thin fluid layer, right? This dimension, this gap is quite thin. And we have two solid plates, one on top and one on the bottom. The force that you apply is essentially linear with the velocity. So this is what was observed. But if you had a different size gap, the slope would be different. So this is, if you had a smaller gap, then it would take more force to move at the same speed. If there was a bigger gap, it would take less force. So that was what was observed. Now, there are some fluids that we see don't actually follow this same pattern. But what was interesting is that if we have a small gap and big gap, we can actually talk about not just the relation of force to velocity, but we can talk about the relationship between shear stress and shear velocity. And that is going to, for a Newtonian fluid, be a straight line. So what is shear stress and what is shear velocity? So shear stress, that would be, we call tau yx. Shear velocity would be du dy. So we'll learn a little bit more in a second exactly what we mean by shear stress and shear velocity. So now there are some fluids that don't behave this way. For non-Newtonian fluids, things are not so simple. We can get fluids that the relationship between shear stress and shear velocity goes like this. That would be something like oobleck. You can also get things that appear too thin. So this would be shear thinning. This is shear thickening, where the fluid appears to get thicker as we start to try to move that top plate faster. There are other things too. You can get fun things that start and and needs some non-zero shear stress to kind of get going, and a whole bunch more. So I'll pull up, just for a quick second, we'll pull up Wikipedia, right? Everybody's favorite. And we can see some of the different types of non-Newtonian behavior that you could see. So this shear thickening, we call it a dilettante. Not super worried about some of the terminology. A shear thinning, that's a pseudoplastic. There are other fun ones too. So you have something like, thixotropic, where the viscosity decreases with the duration of stress. So those are things where there's kind of an alignment in the fluid that changes it, and then the shear rate, the relationship between shear rate or shear velocity and shear stress is actually changing with time. But the take-home message is that there's this relationship between the shear stress and the shear velocity. So let's talk a little bit more about that. We are mostly going to focus on Newtonian fluids here throughout the entire course. We will talk a little bit about some behaviors that are seen specifically in non-Newtonian fluids, but that will be just a small part. Mostly we're talking about Newtonian. Okay, so this was observed, and we have Newton's law of viscosity. So what Newton's law of viscosity says that these two guys, the shear stress, is proportional to the shear rate, and that there's a constant of proportionality. So different fluids are different, but they have a proportionality constant mu. So this equation becomes a very important equation in fluid mechanics. So the viscosity, which is mu, right, a term that you've heard before, it's how thick or thin a fluid is. Strictly speaking, it's the proportionality between shear stress and shear velocity. Shear stress, tau, is the force divided by the area. And shear velocity, this is the slope of velocity, or the velocity gradient. So it's molecules sliding past each other. So what we really need is a difference in the velocity, a difference between the sort of different layers of fluid sliding past each other, and that creates friction. So this is kind of fluid friction, is another way to think about it. It's friction in the neighboring layers of fluid. So one of the somewhat confusing things about viscosity is the units. So we have dynamic viscosity, which is mu, right? This is mu. And we have kinematic viscosity, which is the Greek letter nu. So, right, tons of fun, very close to the same, at least in pronunciation. Dynamic and kinematic, again, both maybe sound kind of the same, but these are two separate and different quantities. The dynamic viscosity is mu, which is, again, this proportionality constant between shear stress and the slope of the velocity, or the shear velocity. The kinematic viscosity, nu, is equal to the dynamic viscosity divided by density. So we'll see, I guess, a little bit why that works. We have some goofy units for all of these things. So a common unit for dynamic viscosity is 1 poise, which is defined as 1 gram per centimeter second. So very strange units. We also sometimes see 1 Pascal times second. So Pascal being the unit of pressure, which is 1 Newton second per meter squared. So all of these are units of dynamic viscosity. They're all goofy. They're all actually interchangeable. They're the same units, even though they look quite strange and quite dissimilar. We also could see like these same units, but in US terms, like pounds force times second divided by foot squared. That would be similar to this guy over here. Kinematic viscosity, the units are a little bit more straightforward. We have units of Stokes, or 1 stoke, which is defined as 1 centimeter squared per second. And this is actually a unit of, this is like a diffusion or diffusion rate. So what kinematic viscosity is going to help us understand is how momentum, or how, right, velocity times mass, momentum, is actually diffusing into a material because of viscosity. And that's going to be something that will take us, I guess, a little bit to unpack really what that means. But it's about an area per time for kinematic viscosity. All right, so they're going to be fun units, but what are some other things that we should know about viscosity? So some values of viscosity. So I'm going to flip over to another slide, and we can see some general things. This is a chart from our textbook, which is talking about the absolute viscosity. So if we want to find viscosity, we can look at this chart and we can note a few things. Obviously, we can see some things like oil, glycerin. These are pretty high numbers. A lot of things that we think of as kind of thin liquids like water and octane and kind of typical organic solvents are kind of in this range here. And then down here, maybe 2 orders of magnitude lower, we see gases. So most gases have pretty similar, very low viscosity. They're very thin. What we think of as kind of thin liquids fall in kind of this range here, over the range of about an order of magnitude. And then these thick oils are, up to a couple orders of magnitude thicker yet. We can also see here at the bottom is temperature. And we can see kind of 2 unique ways that these systems change with temperature. So gases actually get thicker as we increase temperature, where liquids all decrease. They're all getting thinner with higher temperature. And that's really because with gases, we're looking at more molecular collisions, which makes them thicker. And liquids, we're going to be moving faster, and they're going to be a little bit less sticky to each other and going to slide past each other better. So it's really about what's happening at a molecular level, why these effects happen. All right, so we're going to head back and we'll write a few notes on this. Okay, so what can we learn about values of viscosity? So gases have low viscosity. Liquids cover a large range, but are higher than gases. And right, again, this is kind of how thick or thin the substance is. So it follows a trend that's similar to what you would observe. The things that are thick have a high value, but it can range over several orders of magnitude. How does temperature affect it? It affects gases and liquids differently. So we'll write gases and liquids. Right, so gases, as temperature goes up, we get more molecular collisions. So there's actually more interaction and viscosity goes up. For liquids, as temperature goes up, we're not sticking together quite as much. So what that means is viscosity ends up going down for liquids. How does pressure influence viscosity? Typically not a lot. So not as important as temp. It does change it, right? Whether you're a gas or a liquid, it does change it, but not as much as what it does for temperature. So for gases, viscosity increases as pressure increases, but really you have to be, seeing deviations from ideal gas pretty significantly before this starts to become a major effect. So non-ideal gas. For liquids, I'll just give one example. So viscosity increases as pressure increases, but for water, viscosity at 10,000 atmospheres is about 2 times viscosity at 1 atmosphere. So to get a factor of 2 difference, we need to go to a factor of 10,000 difference in pressure. So not a huge effect. There are definitely substances where you can get a larger effect, but typically it's fairly small compared to things like temperature and other processes like that. So we're going to see how we can use this and what we can use specifically this equation up here, Newton's law of viscosity, to help us in our problem solving. So join me on the next video to hear more about that.